In this video, we're going to be discussing how electrons actually fill into the atom, so what rules they use to fill into all of these different shells. We're going to go over as well two different methods that we can use to communicate this information to other people. One of them is a drawing, and one of them is going to be a sort of address system, which is kind of a shorthand. There will be a third system that we're going to use, which we'll go over later in the chapter. But for right now, we're going to start with these two. You are going to need something to write with. You're going to need something to write on. For this, you will need access to a periodic table. Once you have those things ready, let's start. Okay, so to kind of review where we are so far. We took Rutherford's model of the atom and modified it a little bit to make the Bohr model of the atom, which is where you get those concentric rings where each ring is an energy shell. We then broke down those energy shells into component pieces called subshells and orbitals. And then we also talked about how electrons that occupy orbitals have a spin value to them. Right, so our energy shells, the higher the energy shell is, the farther away it is from the nucleus, and every energy shell can hold 2n squared number of electrons, so 2, then 8, then 18, etc., etc. The larger a shell is, the more subshells it can have. The first energy shell is so small it can only have an s subshell, but the third energy shell is much larger, so it's allowed an s, a p, and a d subshell. Right, and each of these subshells broken up into orbitals. Each orbital can have 2 electrons. An orbital is just a place where you can find electrons. S's have 1 orbital, P's 3, D's 5, F's 7. Right, so that's where we are right now. So at this point, we're going to go over the 3 rules that electrons use when they fill in all of these different orbitals and subshells and shells. Okay, so the first of these 3 rules is what's called the alpha. And by the way, I will have slides for each of these rules coming up, so you may want to leave a bit of room underneath. Like for Aufbau, leave a good half a page underneath because you're going to have to draw a diagram. But Aufbau principle, electrons will fill the lowest energy orbital that's available to them. Right, so when it has a choice, it will pick whichever orbital is available that has the lowest energy value, because that puts it closest to the ground state. Then we have a rule that's called Hund's rule. Hund's rule is that if you have a sublevel with multiple orbitals, for example, the p sublevel has 3 orbitals, each orbital gets 1 electron before you go back and double them up. And then our third rule is called the Pauli exclusion principle. And what this basically means is that if you have 2 electrons in an orbital, they have to spin in opposite directions. One has to spin up, the other has to spin down. Okay, so we'll start off with the Aufbau principle. This diagram that's on the right-hand side of the slide, draw this accurately, please. So what I would do, pause the video, draw this diagram, and once you have it drawn, then come back and pick up for the explanation. Okay, so you have this diagram drawn, I'm assuming. The way this diagram works is if you start at the top, so start at the top arrow, if you follow the arrows down, it tells you the energy that the orbitals will fill in from lowest energy to highest energy. So 1s is the lowest energy orbital that you can, or lowest energy sublevel. Then after 1s, that arrow is complete, we go to the next one. Next one goes through 2s. That's the second lowest energy sublevel. Then after 2s, the next arrow goes through 2p, followed by 3s. And then 3p, then 4s, and then 3d. Wait a minute. Why do we have that break there? Why does 3d fill in after 4s? Reason for that is that even though 3d is closer to the nucleus than 4s is, third energy shell is closer than the fourth, there are so many electrons in that 3d sublevel that you get increased repulsion, which means that it's actually at higher energy. Okay, so you do get a break with D's. You also get a break with F's because they tend to move in before that. That has to do that they're different energy, even though you wouldn't expect them to be. Okay, so this diagram gives us the filling order. Follow the arrows from top to bottom. Just follow them in direction from tail to head, and you'll always get the correct filling order. This next slide right here covers our next two rules. Right, so the diagram on the right, what you can see is first electron in the 2p sublevel goes in the first open orbital. The second electron in the 2p sublevel doesn't pair with the first one. It goes into its own empty sublevel. Then the third one goes into its own empty sublevel, so now we have 3 unpaired electrons. Again, when you have this situation where there are multiple orbitals, every orbital gets 1. And then when that happens, right, so once everybody has 1 electron, then when we put in the next one, then you start pairing. So that's what happens in oxygen. The 3 orbitals are already full, so when we put in the 4th electron, that 4th electron has to pair with one of them. And again, notice, the paired electrons spin in opposite directions. The other thing you should notice is that when we draw our arrows, all the arrows for the first electrons point in the same direction. Be consistent with this. It doesn't matter whether your electrons start up or down as long as you are consistent throughout the process. Okay, so these are the 3 rules that we're going to follow. Now, our first method of communicating this using these 3 rules is what we call an orbital diagram. You actually, on the previous slide, saw an example of an orbital diagram. Each orbital is written either as a box, like it was in the previous picture, or just as the line on the bottom without the box. And what you want to do when you draw them is you group them together, right? So p sublevels have 3 orbitals, so I'm going to group those 3 together. If I'm drawing a D, I group those 5 orbitals together. And then what you do is you draw the electrons as arrows. So we follow our 3 rules, draw the electrons as arrows, and we go only as high as we need to go. Now, one thing you'll see me do when I draw is I don't draw full arrows. I draw what are called fish hooks, basically half arrows, because that's what I was taught. If you want to draw full arrows, that is perfectly fine. Okay, so what we're going to do is we're going to use those 3 rules to draw the orbital diagram for the element fluorine. First thing we need to know, how many electrons does a fluorine atom have? Well, the number of electrons are equal to its atomic number, which for F is 9. That means we have to draw 9 arrows. Exactly 9, no more, no less. Now what we're going to do is we're going to go to our Aufbau chart. The first sublevel that fills in, the lowest energy sublevel, is the 1s sublevel. S sublevels have 1 orbital, so I draw 1 horizontal line, or 1 box. And now I'm going to start putting electrons in it. I'm going to make my first electron spin up, so that's my first one. Now I'm going to put in my second electron. The second electron can pair, so I spin that one down. Those are our first 2 electrons. The 1s sublevel is full. Once that's full, we move on to the next one. According to our filling order diagram, that's going to be 2s. All s sublevels have 1 orbital, so I draw a line for 2s. I label it as 2s. My third electron points up. My fourth electron points down. Now the 2s sublevel is filled. After this is the 2p sublevel. P sublevels have 3 orbitals, so I'm going to draw 3 lines. I'm going to label them as 2p, and now I'm going to start putting in more electrons. I have 4 already. 5 is going to go in the first orbital. 6, I have to follow Hund's rule and put it in its own, so 6 goes in the middle. 7 goes in the one on the right. Now that all of them are filled, we're going to go back and pair them up. 8 is going to point down in our first orbital. 9 is going to point down in our second orbital. We have drawn 9 electrons. We're done. Walk away. This is the orbital diagram for the element fluorine. 2 electrons in the 1s, 2 electrons in the 2s, 5 electrons in the 2p, 4 of them are paired up, and 1 of them is by itself. So this is how an orbital diagram works. For larger elements, it's just a little bit more drawing, but you follow the same process. In the next video, I'm going to split this into two. What we're going to go over very quickly is an electron address system, and then we'll go over an example of how to do this for both of them, because I don't want to go over 15 minutes with this. So that's what we will cover in the next video, and we'll pick up from here exactly.